Hi, welcome to section 8.2, which is on multi-stage experiments. This is definitely one of the meatier lessons of the course, especially when it comes to probability. We're going to get a little bit deeper into probability in this section and a little bit more complicated in terms of the calculations. So let's start off. We're going to try to make it a little bit easier to understand just by giving by using this diagram. It's called a tree diagram, and this is a really good way to visually kind of lay out what all your choices are in terms of, what could happen with a probability experiment. Some people I find really do not like trees, but some people really find them helpful. So I would just give them a chance and see. I think for the most part, they're, I think, a definite help. So with example 1, suppose you order lunch and you have a choice of entree. So you've got 5 choices: chicken, beef, turkey, fish, or vegetarian, and we're just going to abbreviate. And then 2 types of sides: potato or salad. Draw a tree diagram to figure out how many possible lunches you can order. Now, if I didn't ask you to draw a tree diagram, if I just said, make a list of all the possibilities, you could start by making just a list. Like I could do chicken and then I could do potato, or I could do chicken and a salad, or I could do fish and potato, or fish and a salad, and you keep going. The downside to this, though, is that it's really easy to forget one. So with the tree, what we can do is we start at the base or the beginning of the tree, which is right here, and we ask ourselves, well, what are the possibilities in terms of entree? So the entree, I'm just going to list those. That's going to be my first level. Oh, I don't need 2 of those. That's going to be my first row. So I'm going to write chicken, beef, turkey, fish, and vegetarian is going to be my entree. And then with each one of those, I can do a potato or a salad. And to use the tree, I want you to imagine, so this is side is going to be this row. I want you to imagine that there's a little ball at the top and you're playing one of those games you might have played when you were little, where there's a little maze and you hold it in your hand and you kind of move the maze around to see if the ball can go through and you can get through the maze. Well, I want you to visualize this ball and all the different ways it could travel through this maze. Well, it could go down this first branch and then this one right here, and that gives us chicken and potato. Or it could go down this branch and then this one right here, and chicken and salad. And we're going to list all of those options out. So beef and potato, beef and salad, or turkey and potato, turkey, salad, fish, potato, fish, salad, and then vegetarian potato, and then vegetarian salad. So we can count them, and there's 10 total choices. Or possibilities, and I could even put brackets around those because this right here, that's my sample space. So you might remember from video 8.1 that when we list out all the different possibilities, that's called the sample space. So for part B, when it asks what's the sample space, well, that's it. Is there a faster way of determining the total possible outcomes without drawing a tree? The answer is yes. So we can use what's called this fundamental counting property, and the math way or the math speak explanation is in the box, but I'm going to explain it in terms of this problem. So if you know that there's an event and there's multi-stages to the event, what you can do is you can take the number of times each stage can occur and just multiply those together to find the total number of possible outcomes. So for example, in this scenario, we have entree as our first sort of stage in our experiment, and my computer's freezing up, of course. Okay, so we've got entree. Bear with me here. So we have entree, there's 5 choices of entree, and then we have sides, and there's 2 choices for sides, and if we multiply those together, we end up getting 10, and it's no coincidence that we get 10. That's how the fundamental counting property works. So The tree still is nice though because it identifies all the specific scenarios. So at this point, if I said, what's the probability of ordering fish in a salad? You could look at the sample space and say, oh, well, that's one outcome out of 10, so the probability of that is 1/10. Whereas just using that counting principle just tells you the total. So it doesn't help you answer individual probability questions, but it does help you if you just want to know the number of total possibilities. So for example 2, this highlights the fundamental counting property, and you could try this on your own. By pausing the video would be a great idea. So it says, suppose you order a new sports car and you have a choice of 8 colors, 2 types of transmission, and 5 interior styles. How many different types of car can you order? So notice they're not asking for probability at all. They just want to know how many different types of car can you order. So in this case, I would use the fundamental counting principle and I would just multiply. So I would take the number of colors, which is 8, and then I would take the number of transmissions, which is 2, and then the number of interior styles, which is 5, and I would multiply those all together, and then we get 80. So that tree would be really, really large. Not impossible, but it would be a really large tree. So this is definitely faster. So in this section, we're going to talk about events that are multi-stage, meaning more than one thing is happening. So for example, we're getting an entree and we're getting a side. So we're doing one thing and then the other. When we're wanting to find the probability of a multi-stage or a sequence of simpler experiments, then you can find the probability by multiplying each part of the experiment, the probability of each part together. So let's look at example 3. So for a test of 8 true-false questions, determine the probabilities of the event. So part A asks, what's the probability of getting the first 2 questions correct? So the first question correct and then the second correct. So what we can do is we can just split that up and say, well, let's find the probability of getting the first question correct, and we'll multiply that by the probability of getting the second question correct. So if it's a true-false, if each question is true-false, then the first question, I have a 1/2 chance of getting that one correct because there's 2 possibilities if it's true-false. And the probability that I get the second one correct is also 1/2 because that's also true-false. So I can multiply those together and I end up getting 1/4. With the second one, we want to know what's the probability of getting the first 5 questions correct. So this one's a little bit longer. So we're going to take the probability of getting the first one correct times the probability of getting the second, I'm just going to do a check mark, seeing that correct, plus the probability of getting a third one correct, plus the probability of the fourth one correct, and then the probability of the fifth correct. And each one of those is 1/2 because there's a 1 out of 2 chance in getting the question correct if it's true false. So I'm going to take 1/2 and multiply it by itself 5 times. A shorter way to do this is by using an exponent. So if you want to use your calculator, I would just take 1/2 and raise it to the 5th power. That will save you some time. Or you could do it by hand. 2 times 2 times 2 times 2 times 2 is 32. And then 1 times itself 5 times is just 1. So the chance of getting all 5 of the first questions correct is 1 out of 32. Now these questions could change, depending on, if you have a different type of test, or maybe there's A, B, C, D, there's a lot of different parameters that can change these types of questions, but hopefully that gives you an idea of how you can use that multiplication principle. Let's do another one, a visual one. So example 4, we're going to consider the 2-stage experiment with these spinners. We're first spinning spinner A, and then we're spinning spinner B. And the first question wants to know what's the probability of spinning a white on the left and then a white on the right. So this and then, that's a clue right there that it's a multi-stage experiment. You're doing more than one thing. So that tells you you're going to multiply those probabilities. So we're going to find, so in general, we're finding the probability of white and then another white on spinner B. So white on spinner A and then another white on spinner B. So we're going to find first the probability of white on A and multiply that by probability of white on B. So I'm going to look at spinner A, and it looks like there's 8 different possibilities, so 8 sections that are equally sized, so the total is going to be out of 8, and there are 2 white sections, so the probability of getting white on A is 2 out of 8, and then the probability of white on B, it looks like there's 1 white section out of 6 equally sized sectors, so it's going to be 1/6, and then we're going to multiply. Now you can cross cancel if you want, so 2 goes into 2 once, it goes into 6 3 times, 1 times 1 is 1, and then 8 times 3 is 24. So you get 1 out of 24. So the probability of spinning a white and a white is very small, 1 out of 24, which is a pretty small decimal. Try the second one on your own. So probability of yellow or red followed by a blue. So I'm going to find probability of yellow or red and multiply that by the probability of spinning a blue. So for the first spinner, whoops, sorry about that. So for this first spinner, it's going to be out of 8 again. Yellow or red, we've got 3 yellow, and then a red makes 4, so 4 out of 8, times, not plus, I almost put a plus there, so it's going to be times probability of blue on the second one. So that's going to be, there's 1 sector of blue, so 1 out of 6, and you're multiplying those. And again, you can cross cancel if you'd like. So 2 goes into 4 2 times, 2 goes into 6 3 times. 2 times 1 is 2, and then 8 times 3 is 24. And then we could have actually reduced this 2 over 8, but you can see in the end here we can reduce 2 over 24 by 2 and get 1/12 by dividing each of these by 2. So the probability here in the end is 1/12. And if you're not a fan of cross canceling, if you like to just multiply and reduce all the way in the end, that works too. So this next part we're going to do, it's called a probability tree diagram, which I know you're probably thinking we just did a tree diagram. Well, probability to I can't talk. A probability tree diagram is just a tree diagram where we write the probabilities on each branch. So in this case, we're going to simulate flipping a coin heads or tails 3 times. So I want you to imagine a coin, and it's got head on one side and then it's got tail on the other, and we're going to flip it. So when we start the experiment, we flip the coin, and it could either be heads or it could be tails. So this first row represents my first flip. And then the second row represents my second flip. So if I get a heads first, then my second flip could either be heads or tails. If I do a tail first, then my second flip could either be heads or tails. Now to make it a probability tree diagram, as I'm going here, let's write the probabilities. So the probability of getting a heads first is a half. Probability of getting a tails first is a half. Now after I flip it once and I flip it again, those probabilities don't change. The probability of a coin, no matter how many times I flip it, is always a half. So then I keep going. So when I'm at this place, so let's say I get a head and then a head, well, I could get a head or a tail on that last flip, and these are a half also. Right here, I could be a head or a tail, and these are probabilities are a half. I could get a head or a tail, and these are a half. I could get a head or a tail, and these are also a half. Now, what we could do here is we could write out the sample space, and that's a list of all the possible outcomes. So remember, you could just go down the tree. For example, we could start at the top and go heads, heads, heads. So that's the first option, and I'm going to check that off so I know that I went down that one. And then heads, heads, tails. So heads, heads, tails. And then heads, tails, heads. Heads, tails, heads. And then heads, tails, tails. So heads, tails, tails. And then I'm going to go tails, head, head. Tails, head, head. Tails, head, tails. Tails, head, tails. Tails, tails, head, and then tails, tails, tails. And I should have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that exhausts my sample space. Now with this question, we have 8 equally likely outcomes. When you have equally likely outcomes and you're asked a probability question, you can just look at the sample space and say any probability is going to be out of 8, and you can just count which ones apply and get the probability. This only works because they are equally likely outcomes. We're going to do an example next where the outcomes are not equally likely, and you will see the difference. If you wanted to, you could use this probability tree diagram and multiply to get the probability. So for example, let's say you want the probability of head, head, head. One way to do this is to go down the tree and multiply as you go. So you start at the top and you say, okay, 1/2 is the probability that I get the first head, times 1/2 is the probability that I get the second head, times 1/2 is the probability that I get the third head, and I multiply those out, and I get 1/8 as that probability. Well, the other option is you look and you see there's 8 equally likely outcomes. Head, head, head is one of them. So the probability of head, head, head is 1/8. It's a lot faster to do it this second way. And since they're equally likely, we are allowed to do it that way. It's not going to work for every single problem, but for this one it does. So let's go ahead, and this would be a great place. Pause the video and try A, B, and C on your own. So A, you flip 2 heads and 1 tail in any order. So what's the probability of that happening? So 2 heads and 1 tail. So I'm going to go ahead and count, and I'm going to use green here. So 2 heads and 1 tail. So this outcome, and it looks like this outcome. So it looks like there's 3 different outcomes there. So the probability is 3/8. Okay. I'm going to go ahead and erase that and do the next one. So the next one says you flip only 1 tail. So I'm going to look at the outcomes where there's 1 tail. So I've got 1 tail here, I've got 1 tail here, and I've got 1 tail there. So my answer again is 3/8. And then the last one, you flip at least 1 head. So anytime you see the words at least and it's a probability question, it makes it harder because at least means you could have 1 head, or you could have 2, or you could have 3, and so you're counting up quite a bit. So one way, it says hint use complementary events. We'll do that in a second, but I'll show you both ways. So at least a head would be 3 heads, 2 heads. 2 heads would count. This would be at least a head. Any option where there's at least 1 head, we're going to count. So there's 7 out of 8. That have at least a head. The other thing that we can do is we can use complementary events, and the way this works is we take the probability of something happening, so the probability of getting at least 1 head is, I'm just going to erase this 7/8, whoops, and it's going to erase all of that, I guess. At least 1 head is the probability is 1 minus the probability of getting no heads. And the reason this works is, think about, for instance, the probability of it not snowing versus the probability that it's going to snow. If there is a 70% chance that it's not going to snow today, then there's a 1 minus 0.30 chance, so there would be a 30% chance of it snowing. So the probability of it snowing and not snowing, those probabilities need to add to 100%. So we call them complements. So if it's easier to find the complement and just subtract it from 1, then sometimes that's the way to do it. So in this case, if there's one event where there's not at least 1 head, then we can just say, well, what's 1 minus 1/8? Well, that's 7/8. And that's the same answer we got by counting all of those other outcomes and getting 7. So you don't have to use this method for this question. It's just an option. So the next example, this is probably the most in-depth example that we're going to get into in terms of probability. And this is more in-depth than the last one because we've got a scenario where the probabilities are not all going to be the same. So imagine that you have 10 socks in a drawer, 5 black socks, 3 gray, and 2 tan. If you are a visual person, it would be a really great idea for you to take a piece of paper right now and divide the piece of paper up into squares and make 5 black If you want, you can even make them in the shape of socks, but you don't have to. So make 5 black squares, and then 3 gray, and then 2 tan. So you have 10 pieces of paper in front of you on your desk. And so when we go through the experiment, you can actually move those around and pretend like you're selecting the color socks that we're supposed to be selecting. So it says draw a probability tree diagram to represent the choice of 2 socks without replacement. This is important. So it means that when you pick up the first sock, you're putting it away, or maybe you're putting it on. You're not putting it back in the drawer. And then you're picking up another sock. So, and this actually, which means that you do not, that should say do not replace the first sock after you pick it up and pick another. So let's start by making our first layer of our tree. So we're going to first pick a sock. So our first pick, and I'm going to make this really wide so I have lots of room because it's going to be a bigger tree. So my first sock could either be black, or it could be gray, or it could be tan. And we're going to make this a probability tree diagram. So the probability of me picking a black sock, if we come over here to our visual, there are 5 black socks out of 10 total. So I'm going to write 5/10, and I'm just going to erase this do not here just so I have a little bit more room. There we go. So the probability of me picking a gray sock would be 3 out of 10, and the probability of me picking a tan is 2 out of 10. So now I go down each layer, and then I'm going to pick a second sock. So I go down this first branch. If I pick a black first, then I could, so that would be like me crossing this off here. I picked a black first. So now what are my choices? Well, I could pick another black, I could pick a gray, or I could pick a tan. Well, if I pick another black, then there are 9 socks now because I already picked a black. So there are 9 socks total. So all of these are going to be out of 9. There are 1, 2, 3, 4 blacks left because I already picked one. There are 3 gray, and there are 2 tan. And if you notice, what do all these fractions add up to? So 4 plus 3 plus 2, that is 9 out of 9, which is 100%. Or up here, 5 plus 3 plus 2 is 10. 10 out of 10, they equal 100%. So you always want that to be the case. So now I'm going to unerase that black sock because now I'm going to go down the second branch. I'm going to pretend that I picked a gray first. So I'm going to cross off a gray. If I pick a gray first, then I've got some choices for my second pick. So I could pick a black sock next, or a gray, or a tan. Well, there are 5 blacks left over out of 9 total. There are 2 gray, since I already picked one, out of 9 left, and there are 2 tans out of 9 left. And then I'm going to put that gray one back, and I'm going to go ahead and pick a tan first. So I'm going to cross off a tan. And if you have these on pieces of paper in front of you, you take the tan out, like you take it aside as if you're picking it. So now I've got black left, I've got gray, and I've got tan. So there's 5 black out of 9, there's 3 gray out of 9 left, and there's 1 tan out of 9. And it is possible sometimes with experiments there might not be any left of something, and if that's the case, you put a 0, which represents the probability of 0. So from here, what you can do, if you want to be really thorough with your tree, which is kind of how I like to do it because it sets me up for doing really well in the probability questions, I go down each branch one at a time and I find the probabilities. So for instance, I go down this first branch, a black and a black. So the probability of black and black. I multiply 5/10 times 4/9. So 5/10 times 4/9. And I'm going to multiply straight across. So 5 times 4 is 20 over 90. Now here's the thing. I know normally I say reduce your fractions. In this case, don't. Reduce at the very end, because if you have to add anything, it makes it easier for them to have common denominators. So now I'm going to go down the second. So the first branch is black and then gray. So the probability of black and gray is going to be 5/10 times 3/9. So 5 times 3 is 15, 10 times 9 is 90. And then this last one is going to be black tan. So probability of black tan is going to be 5/10 times 2/9, and that gives me 10/90. Now, hopefully you get the hang of this here. So if you want to pause the video and try the rest on your own, you can, or just mute me. So I'm going to go ahead and do the rest. So gray black, so the probability of gray black is going to be 3/10 times 5/9. So 15/90. And then gray gray, so probability of gray gray is 3/10 times 2/9. So 3/10 times 2/9 is 6/90. So notice these are all out of 90. Gray tan, so probability of getting a gray and then a tan is 3/10 times 2/9. 3 times 2 is 6/90. The last third here, so tan black, so probability of tan black would be 2/10 times 5/9. So that's 10/90. And then tan gray, so probability of tan gray would be 2/10 times 3/9. So 6/90. And then last, tan, so probability of picking 2 tan socks would be 2/10 times 1/9. So 2 out of 90. So really small chance of picking 2 tan socks that match. So now what you could do if you really want to be thorough, which is a great idea, is you add all these numerators. These should add up to 90/90. So if you add these, we've got 20, that's 30, and 15, that's another 30. So we've got 60 there, and then we've got 70, and then we've got 3 sixes, and a 2 would be 20, so that would be 90/90. So if I add those all up, I get 90/90. So that means I did all of my multiplication correctly. So now the great thing is, I know you're probably thinking that was a ton of work, and it is, but now when you're asked the probability questions, you're all set to go. So A says, what's the probability of you picking a black and a black? We'll find probability of black and a black, and that's that first fraction, which is 20 out of 90. So we've answered that. My computer's freezing, but I'll go ahead and talk us through this. So that first answer for A should be 20 out of 90. And then at this point, you can go ahead and you can reduce that to 2/9 and circle 2/9 as your final answer. For the second one, so it says you pick one black and one tan. Well, that could either be black tan or tan black. So if there's ever multiple scenarios that fit the question, then you're going to go ahead and add those probabilities together. So you're going to find BT and then find the probability of TB, tan black, and you're going to add those probabilities together. So probability of black tan, we said was 10/90. So that's right here. So we've got 10/90 plus, and then tan black is over here is 10/90 also 10/90. So we end up getting 20 out of 90, and we can reduce that by dividing each of these by 10 and getting 2/9. And then just to go back, that first answer that I wasn't able to write down because my computer was freezing, you can divide those both by 10 and get 2/9. And then this last one, this is a really lengthy, this is probably the hardest probability question that you could get. You pick at least one gray sock. So that means a gray black or a black gray or a gray gray, tan gray or gray tan, anything with gray in it. So we're going to go ahead and pull all of those fractions. We've already done the work. So gray black, I find that one. So gray black is 15/90. Black gray, we said was 15/90. Gray gray, gray is 6/90. Tan gray is 6/90. And then gray tan is 6/90. And then we add all those together. And this is why it's great that we did not simplify, because we've already got a common denominator. So you've got 15 and 15 is 30 plus, it looks like we've got 3 sixes, which is 18. So that would be 48 out of 90 there. And then we could reduce that by a factor of 4. So we could divide each of these by 4. You could start by dividing it by 2 if you weren't sure. So you do that, you get 24 out of 45. And then you divide that, oh, you know what, it's not a factor of 4, because then you can divide these both by 3. So That was actually a factor of 6 we could have divided in the beginning. So we should get 8, and then 45 divided by 3 is 15. So your final answer is 8 over 15 there. But the key is really setting up that tree, and then that way you can go and add anything that's possible. So if you're a person that likes step-by-step instructions, below are your step-by-step instructions. So these, make a tree diagram. We're multiplying to go down the tree. So multiply to going down the tree to get the probability. And then if you're asked the probability of multiple different outcomes, you're going to add those together. So the next part, we're going to talk about independent versus dependent events. Sometimes when you do probability, like in that last example, that first event, the fact that I picked a sock and I didn't put it back, it affects me picking that second sock, because you notice, like if you look at the tree, when I picked a sock, the probabilities changed on those second branches. They now became out of 9 instead of 10. Whereas in my flipping the coin example, they were all 1/2. So those I would say are independent events, the coin example, because the first flip of the coin doesn't affect the probability of the other. So when we say that an event affects the probability of the other one happening, then we call them dependent events. And anytime you have a scenario where something is not replaced, it's going to be a dependent event. So that's also like the sock example above. The fact that you pick it and you put it to the side and you don't put it back, you're changing the scenario. If one event, the probability of it happening does not affect the probability of another, then we say they're independent events. So like flipping a coin, you could flip a coin 1,000 times and it does not matter what the results are for those first 1,000 times. That 1,001th time is not going to be affected by those first flips. So sometimes there's a formula that's helpful for the test for independence. We're going to come back to that. We're going to do an example and then we'll come back to this formula. So let's do example 7 first. So we're going to classify the events as dependent or independent and then find the probability. So go ahead and pause the video and try this on your own. So this first example, rolling 2 dice and getting a sum of 2 in succession. So you want to think about, well, what does it look like when you roll two dice? So what are the possibilities in terms of outcomes? And I'll go ahead and send you guys, I've got a nice little sheet, or actually you could even just Google what it looks like when you roll 2 dice. And you know what? I'll go ahead and do that right now so you can see. Okay, so I just Googled sample space for rolling 2 die and I got this nice chart. So basically all of these the outcomes where you see the parentheses, it looks like ordered pairs. These are all the possibilities. So there's 36 different possibilities. There's 6 by 6, so 36 total. So this first one, for example, means you roll a 1 and a 1, or a 1 and a 2, or a 2 and a 1. So those are all the possibilities for rolling 2 dice. So the first question is, when you roll 2 dice, are those events independent? So if you roll a die, does that affect the probability of rolling something on the second die? And the answer is no, they don't affect each other. So they're independent events. So for that very first example, we should write independent. So they're independent events. And then we want to know, what's the probability of rolling 2 dice and getting a sum of 2 in succession? So let's break that down. So we're going to take the probability of getting a sum of 2 the first time, and then what's the chance of me rolling a sum of 2 again? So let's go back and I'm going to look at that chart again. So what outcomes result in a sum of 2? There's only one. If I roll a 1 and a 1, so there's a 1 out of 36 chance that I get a sum of 2 if I roll 2 dice. So 1 out of 36. So I'm going to take 1 out of 36 of me getting a sum of 2, and then 1 out of 36 of me getting a sum of 2. And so if I multiply those together, I get 1 out of 1,296. Okay, so if you have 2 die in your hand, you roll them, and then you roll them again, the chance of you getting a sum of 2 and then a sum of 2, or 2 ones is 1 out of 1,296. So really, really teeny tiny chance of that happening. Okay, second example. So selecting 2 white balls from a bag of 3 white, 2 yellow, and 5 red if the first ball selected is not replaced. So if you're picking a ball, let me just diagram this first. So we got 3 white and 2 yellow and 5 red. Okay, so there's our bag of balls. And if you're picking one and then you're not replacing it and then you're picking another, then that would be dependent. And you know what, I'm looking, I said independent, but wrote dependent for that first example. That should be independent. These are dependent. And they're dependent because of the fact that it's not replaced. So let's find the probability. So what's the probability of selecting 2 white? So let's do probability of selecting a white first times the probability of selecting a white on the second pull. So when I first select a ball, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different choices, and there's 3 white choices. Now, if I pick a white, I'm going to cross that off. There are on the second go around, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different choices, and there are 2 that are white. So if I multiply 3 times 2, I get 6, and then 10 times 9 is 90, so I get 6 over 90, and I can divide, both of those are divisible by 6, and I get 1 over 15. So you'll notice that with dependent events, sometimes, a lot of times, that second fraction, the denominator ends up changing, just like the sock example, because whatever I did that first stage affected what I did on that second stage. So it's not anything for this one that you have to use a formula for. You just want to think through it. So with example 8, we're actually going to use the formula on the previous page. So take a minute and read example 8 to yourself. You can pause the video, and then I'm going to go ahead and I'm going to write down the formula from the previous page. So the previous page, and what I mean, I'll just scroll up so you can see what I mean, this test for independence. So I'm going to write that down. So the test says that if A and B are independent, then this is true. The probability of A intersect B, so that's and, the probability of both of them happening at the same time, should be the probability of the one times the probability of the other. If it's not, then it means they're not independent. So let's go ahead and test this, because this question asks if these are independent events, if the chemicals and thermal pollution of streams are independent events. So it says that 6% of the streams suffer both chemical and thermal pollution. So both, that's going to be your A intersect B. So your 6% is going to go right here. And then for A, I'm just going to call A chemical pollution. So we'll call A, I'll write 40% for that one. So 40% times, and then B is going to be thermal pollution. So I'll say 30%. And if you want, you can make those decimals. So we can say 0.40 times 0.30 should be 0.606 if those are independent events, and it's not. So 0.40 times 0.30 ends up being 0.12. So they're not the same. So these events are not independent. And what this means in terms of a practical application is that this chemical pollution and the thermal pollution, they influence each other. And so if there's more chemical pollution, it's probably going to influence more thermal and vice versa. And that's something to definitely take into consideration if you're working at trying to eliminate these problems. So let's look at the next one. So using complementary events to solve a more complicated probability problem. So like I said, we did this one with the flipping the coins I mentioned using complementary events. And if you remember, you can always take 1 and subtract the probability of something never happening. So 1 minus the probability of something never happening. that's going to be the same as the probability of at least once. So that's just the general framework that you can use. So in this question, it says if a die is tossed 5 times, so die meaning like a dice that has 1, 2, 3, 4, 5, and 6 as choices, what's the probability of obtaining at least 1 6? Now, if you did a tree for this and actually diagrammed rolling a die 5 times, it would be a gigantic tree. It would be nearly impossible. It would take forever to go through that tree. Imagine that sock problem, only, 5 times as big, and going through every outcome that had at least a 6. It would be ridiculous. So instead of doing that, we're going to just try to find the probability of never getting a 6. Because if we can do that, we can do 1 minus the probability of never getting a 6, and that's going to give us the probability of at least 1 6. So how do we find the probability of never getting a 6? Well, never getting a 6, if we think about the choices. So when we roll a die, we can get a 1, 2, 3, 4, 5, or 6. So the probability of not getting a 6 is going to be 5 out of 6. But we're not just rolling it once, we're doing it 5 times. So it's going to be 5 6 times 5 6 times 5 6 times 5 6 times 5 6, because we're rolling this, it's being tossed 5 times. So we need to take 1 minus all of that, and that's going to give us our answer. And then with the calculator, you can just do 5 6 to the 5th power if you want. So 1 minus 5 6 to the 5th power, and that'll be an easier way to do it. And if we round to 4 decimal places, I'm going to use a squiggly equals, we end up getting approximately 0.5981 for our answer. So we've got one more example left, and this is a different concept called expected value. And expected value is just basically, it's basically like the average of what could happen. And a lot of times expected value, we use expected value to find like in general, like the average that you could win or lose from a game. And so that's what this example 10 is all about. So go ahead and read that. You can pause the video and read that on your own. And then I'm going to go ahead and walk you through it. So the formula for expected value is in the box below. And basically what we're going to do is you take the probability of something happening times the outcome plus the probability of another event times the outcome. And by outcome, I mean like the value. Like, so if you're winning, it's going to be positive. If you're losing, it's going to be negative. So the expected value or the expected earnings of this lottery ticket are going to be the value for the ticket. So $50 is one possible earning. Okay, times the probability of that happening. Well, the probability of winning 50 bucks is 1 over 500. So that's the first scenario. The second scenario would be $20 and 1 over 200. So I could win $20 with the probability of 1 over 200. Or I could win $5. I don't know why my eraser is being funny. Oh, and now it's erasing what I don't want it to erase. So I could win $5 with a probability of 1 over 50. Or I could win $1 with a probability of 1/10. And then I could, there's also a $10 bonus that's possible, so 10 bucks, and the probability of winning the bonus is 1 out of 200. So again, if a possibility were to lose money at any point, then I'd put a negative near any dollar amount that represented losing. And so I go ahead and I put all of that in my calculator, and then, or you could do by hand, which is fine too. And you end up getting you end up getting, I wrote 27 or 20th, but that doesn't make sense because I also wrote 45 cents. You know what, let me go ahead and I will pull up, I'm just looking at my answer key. Let's go ahead and I'm going to actually put these in the calculator and I'll show you how to do it. So 50 times, well, you probably know how to do it, but I'll just demonstrate it just in case you want to see it. Plus, and then we're going to go 20 times 1 divided by 200 plus 5 times 1 over 50 plus, I don't even have to do the 1. You could do 1 times 1/10, but no need to put the 1 there. And then 10 times 1 over 200. Enter. Okay, and we get 45 cents. And so 0.45. And the reason I say 45 cents is because, when we're dealing with money here, I'll interpret it financially. So that would mean on average, you're going to earn about 45 cents. So on average, you earn 45 cents per game. Now, here's the thing. Are you ever going to actually earn 45 cents? No. You're either going to win 50, 20, $5, $1, or $10. But on average, if we average that all out, you're going to earn 45 cents. Now, if each ticket costs $1, will the player who regularly buys the ticket gain or lose money over time? Well, if you have to pay money to play, then you take that expected value, which is 45 cents, and you have to subtract the cost to play. And you can actually write that in the box down here. And there's not always a cost to play, but sometimes there is. And so if you subtract the cost to play, we end up getting negative 0.55. So in this case, on average, if you're paying to play, you're going to lose 55 cents per game. And again, are you ever going to lose exactly 55 cents? No, you're either going to lose, there's different scenarios of what you're going to lose, but if we average that all out, you're losing. So with any casino game, they're all going to be negative expected value. Every single game at a casino is going to be negative because that's how they stay in business. So on average, every single person is going to lose. Now, does every person always lose? No. And that's how they get people to come back, because sometimes there are winners. But if we average it out, everybody loses. So I hope that helps. Definitely let me know if you have any questions as you're doing the homework.